welcome to this problem walkthrough. In this session, we'll explore an intriguing coding challenge that tests both your problem-solving skills and your understanding of algorithms. Get ready to dive in and gain some valuable insights. In this problem, you are tasked with analyzing a list of integers and finding a specific solution based on a given target value. The input to the problem consists of two components. First, there is the list of integers, where each element represents a numeric value. Second, there is the target value, which is a single integer. Your goal is to perform an operation on the list to determine the desired output. Depending on the problem's requirements, the output could be a single integer or a list. For example, if the operation involves identifying indices or values within the list that satisfy the target condition, the output would reflect that. This forms the foundation of the problem definition. Now, let's look at some examples to clarify the operation. In the first example, the input list is 2, 7, 11, 15, and the target value is 9. The output is 0, 1, which represents the indices of the numbers 2 and 7. These numbers add up to the target value of 9, making them the solution. In the second example, the input list is 3, 2, 4, and the target is 6. Here, the output is 1, 2, as the numbers at these indices, namely 2 and 4, sum to the target value. These examples illustrate the type of reasoning required to arrive at the correct output. Let's consider one more example. In this case, the input list is 3, 3, and the target is 6. The output is 0, 1, indicating that the numbers at indices 0 and 1, which are both 3, add up to the target. This example highlights that the solution can include the same number twice, provided it appears at different indices. Additionally, the problem comes with specific constraints. For instance, the input list will always contain at least 2 elements and at most 10,000. Each number in the list will be a non-negative integer, ranging up to 1 billion. Similarly, the target value will also fall within this range, and importantly, there is always exactly one solution. However, the same element cannot be reused within the solution, ensuring that each index is used only once. Finally, let's discuss edge cases and additional notes. Edge cases include scenarios like the smallest possible input list, such as data equals 1, 2, with target equals 3. Here, the solution involves the only 2 numbers in the list. Another edge case involves very large numbers near the upper constraint, such as data equals 10 to the power of 9, 1, 1, with target equals 10^9. In these cases, the solution must handle the computational limits efficiently. You might also encounter lists where multiple pairs of numbers sum to the target, but only one valid pair should be returned. Since the problem guarantees a solution, there's no need to handle cases with no valid pairs. Efficiency is key, as the solution must ideally run in O(n) time complexity, and a hash map is a common tool used to achieve this. With these considerations in mind, you are equipped to approach the problem systematically. When tackling any problem, the brute force approach is often the most intuitive starting point. This method involves exploring all possible solutions, ensuring that each one is checked against the problem's constraints. While this guarantees correctness, it is computationally expensive and becomes impractical for larger inputs. A key observation here is that brute force is straightforward to implement and can serve as a reliable baseline for validating smaller test cases. However, its lack of optimization means that time complexity can easily reach O(n²), or worse, depending on the problem. The trade-off is clear: although it's simple and always available, this approach is not scalable for larger datasets. To address this, we can consider more efficient strategies, such as leveraging pre-processing techniques. Pre-processing the input data is a powerful way to optimize performance by eliminating redundant calculations before the core logic begins. For instance, methods like sorting, hashing, or using prefix sums can significantly simplify operations later in the process. The key insight here is that pre-processing often reduces the complexity of repeated calculations, making it especially useful for problems involving search operations, aggregation, or range queries. The time complexity of pre-processing typically depends on the specific technique, such as O(n log n) for sorting or O(n) for hashing and prefix sums, while subsequent operations are often reduced to O(n) or even O log n when using efficient data structures. While pre-processing does require additional memory and upfront computation, the benefits in runtime efficiency for repeated queries often outweigh these costs. For problems involving overlapping subproblems and optimal substructure, dynamic programming provides another alternative. The strategy chosen here is the optimized approach using pre-processing. This method balances efficiency and simplicity, making it well-suited for a wide range of problems. By pre-processing the data, such as through sorting or hashing, we can often reduce the complexity of brute force solutions from O(n) squared to O(n) log n, or even O(n), depending on the implementation. The key realization here was recognizing that pre-processing eliminates redundant work, leading to significant performance improvements. For instance, sorting data upfront or utilizing a hash map can streamline computations for tasks like searching or aggregating values. Compared to brute force, this approach is far more scalable, and compared to dynamic programming, it is simpler to implement and less memory intensive. However, it's important to note that pre-processing may not be applicable to every problem type, especially those requiring intricate relationships between subproblems. The pre-processing approach was ultimately selected because it offers a versatile and efficient solution for many types of problems. It strikes a balance between performance, memory usage, and implementation complexity, avoiding the scalability issues inherent to brute force while also sidestepping the higher memory demands of dynamic programming. By focusing on pre-processing, we can handle a variety of tasks efficiently, whether through sorting, hashing, or other techniques. This method provides a practical framework for reducing runtime complexity, making it a reliable choice for problems where computational efficiency is a priority. Overall, the pre-processing approach demonstrates how thoughtful preparation of input data can lead to cleaner, faster, and more manageable solutions. To tackle the problem of finding the maximum sum of any contiguous subarray in a given array, we start by defining two key variables, max_current and max_global. Max_current represents the maximum sum of a subarray that ends at the current index, while max_global keeps track of the highest sum seen across all subarrays so far. Both of these variables are initialized to the first element of the array, A0. This initialization ensures that even if the array contains only one element, the algorithm will still return the correct result. By starting the process in this way, we lay the groundwork for an efficient and robust solution to the problem. Now, we iterate through the array, starting from the second element at index 1. For each element I, we update max_current to either the current element alone or the current element added to the previous max_current. This decision is made using the formula max_current equals max, max_current plus I. The intuition here is simple. At every step, we decide whether it's better to start a new subarray at I, or to extend the existing subarray. Once max_current is updated, we compare it with max_global using the formula max_global equals max_global, max_current, to ensure that we're always tracking the largest sum encountered so far. By the end of this loop, max_global holds the maximum sum of any contiguous subarray. This approach is efficient because it avoids the need to explicitly generate all possible subarrays, instead calculating their sums dynamically. The efficiency of this algorithm comes from three key insights. First, the greedy choice at each step, whether to start a new subarray or extend the existing one, allows us to maintain an optimal solution without backtracking. Second, the distinction between local and global optima is crucial. Max_current tracks the best sum ending at the current index, while max_global ensures we don't miss the overall maximum. Finally, the algorithm handles negative numbers effectively. If extending a subarray results in a negative max_current, it resets to the current element, discarding any subarray that would decrease the sum. This design ensures that the algorithm remains efficient and accurate for any combination of positive, negative, or zero values. By using simple variables like max_current and max_global, we achieve constant space complexity, making this approach not only fast but also space efficient. At the core of this algorithm are two primary operations, comparisons and a single pass through the array. Each comparison, such as those performed by the max function, determines whether to start a new subarray or extend the current one. These are constant time operations, O(1), and occur once for each element. Additionally, the algorithm processes the entire array in a single loop, ensuring a linear time complexity of O(n). This combination of efficient comparisons and a single traversal of the input makes the algorithm highly performant. On the space side, only two variables, max_current and max_global, are used throughout the process. This ensures that the algorithm operates with a space complexity of O(1), regardless of the array size. Together, these characteristics make it an optimal solution for this problem. This algorithm gracefully handles edge cases that often complicate subarray problems. For instance, in arrays where all elements are negative, such as -1, -2, -3, -4, the algorithm correctly identifies the maximum subarray as the single largest element, in this case, -1. For single-element arrays, whether the element is positive or negative, like 5 or -5, the algorithm simply returns that element as the maximum sum. Arrays containing zeros, such as 0, -1, 2, -3, 0, 4, are handled seamlessly. Zeros neither interrupt the process nor distort the sum calculations. These examples highlight the robustness of the algorithm, ensuring that it consistently produces the correct result regardless of the input configuration. This code solves the problem of finding the maximum sum of any contiguous subarray in an array of integers. The algorithm implemented here is Cadon's algorithm, which operates efficiently in O(n) time complexity. Here's how it works step by step. 1. Edge case handling. The function first checks if the input array is empty. If it is, the function returns 0 since there are no elements to consider. 2. Initialization. Two variables are initialized. Max_current keeps track of the maximum sum of the subarray ending at the current index. Max_global stores the maximum sum found across all subarrays examined so far. Both are initially set to the first element of the array. 3. Iterating through the array. Starting from the second element, index 1, the algorithm iterates through the array. At each step, max_current is updated to be either the current element, nums, I, or the sum of max_current and the current element. This ensures that we either extend the current subarray or start a new one, depending on which yields a higher sum. If the updated max_current is greater than max_global, max_global is updated to reflect the new maximum sum encountered. 4. Result. After processing all elements, max_global contains the maximum sum of any contiguous subarray in the input array, which is returned as the result. This implementation is efficient and concise, requiring only O(1) additional space and ensuring that the solution scales well even for large arrays. This is the Java implementation of the same logic as the provided Python code. The solution uses Cadon's algorithm to find the maximum subarray sum. Key differences include Java's requirement for type declarations and the use of math.max for comparisons. The class structure is straightforward, with the main method for calculating the result encapsulated within the solution class. This implementation handles edge cases such as empty input arrays. In this example, we are given a mix of positive and negative numbers in the array nums. The goal is to find the contiguous subarray with the maximum sum. We start by initializing two variables, max_current and max_global, both set to the first element of the array, which is -2. These variables will help us keep track of the maximum sum of the current subarray and the overall maximum sum found so far, respectively. Now, as we iterate through the array starting from index 1, we calculate max_current as the maximum of the current element or the sum of the current element with the previous max_current. This choice ensures that we either start a new subarray at the current index or continue the previous subarray by adding the current value. At each step, we also update max_global to be the maximum of itself or the updated max_current. For instance, at index 1, the number is 1. Adding it to -2 results in -1, but taking 1 alone gives a higher value, so max_current becomes 1, and max_global is updated to 1. This process is repeated for each index, updating the values accordingly to find the maximum subarray sum. Continuing with the computation, at index 4 where the value is -1, we calculate max_current as the maximum of -1 or the sum of 4(1), which equals 3. Here, the sum of the previous subarray with the current value is greater, so max_current becomes 3, while max_global remains 4 as it still represents the overall maximum sum. At index 5, the value 2 is added to max_current, resulting in a new value of 5, which updates both max_current and max_global to 5. Next, at index 6, the value 1 further increases the sum to 6, updating max_global to this new maximum value. However, at index 7, adding -5 results in a drop in max_current to 1, though max_global remains 6 since the overall maximum has not been surpassed. Finally, at index 8, adding 4 raises max_current to 5, but this still does not exceed the max_global of 6. By the end of the iteration, the maximum contiguous subarray sum for this example is confirmed to be 6. The final output for this example is 6, as the maximum sum of any contiguous subarray in the given array is achieved by the subarray 4, -1, 2, 1. This demonstrates how the algorithm dynamically evaluates each possible subarray and efficiently determines the optimal solution. Now, let's look at a simpler case where all the numbers in the array are positive. In this second example, the input array consists entirely of positive numbers 1, 2, 3, 4, 5. Since all numbers are positive, the maximum sum will naturally come from including all elements in the array. We start by initializing max_current and max_global to the first element, which is 1. As we iterate through the array, we update max_current by adding each element to the running sum, and max_global is updated to reflect the growing maximum sum. At index 1, adding 2 gives a max_current of 3, which updates max_global to 3. Similarly, at index 2, adding 3 results in max_current of 6, which becomes the new max_global. This process continues, with each step further increasing both max_current and max_global. By the end of the array, the total sum of 15 is the maximum subarray sum, as it includes all elements. Now, let's consider a more challenging case where all the numbers in the array are negative, -1, -2, -3, -4. In this scenario, the algorithm still works by identifying the maximum possible subarray sum, but since all numbers are negative, the optimal solution will simply be the largest single number in the array. We start by initializing max_current and max_global to the first element, -1. As we iterate through the array, we calculate max_current as the maximum of the current element or the sum of the current element with the previous max_current. However, since adding 2 negative numbers always results in a smaller value, max_current is updated to the current element at each step. Consequently, max_global remains -1 throughout the iteration, as it is the least negative value and represents the maximum sum achievable. The final output for this example is -1, as this is the largest value among the negative numbers in the array. This case highlights the robustness of the algorithm, which can handle both negative and positive inputs by dynamically adjusting its calculations to find the optimal solution. Whether the input contains a mix of numbers, all positives, or all negatives, the approach guarantees the correct result by leveraging efficient comparisons and updates. Here, we analyze the time complexity of the solution, which is based on Cadon's algorithm. First, the algorithm initializes 2 variables, max_current and max_global, both set to the first element of the array. Since this is a single operation, it takes constant time, or O1. Next, it iterates through the rest of the array, starting from the second element. If the array has n elements, this loop will run n1 times. For each iteration, the algorithm updates max_current by comparing the current element with the sum of max_current and the current element. This involves one addition and one comparison, each of which takes constant time, or O1. It then updates max_global if max_current is greater, which involves another comparison, also O1. Since each loop iteration involves a constant amount of work and the loop runs n1 times, the total cost of the loop is O(n). Finally, the algorithm returns max_global, which is another constant time operation. Adding everything together, the overall time complexity of the algorithm is O(n). Now let's discuss the space complexity. The algorithm is highly space efficient because it only uses 2 variables, max_current and max_global, to store intermediate results. These variables require constant space regardless of the size of the input array, which means the space complexity is O(1). No additional data structures or recursive calls are involved, so the memory usage remains fixed. To highlight how efficient this approach is, let's compare it with a brute force solution. In the naive method, we would generate all possible subarrays and calculate their sums. For an array of size n, the number of subarrays is O(n) squared, and calculating the sum of each subarray could take up to O(n) time, leading to a total time complexity of O(n) cubed. The space complexity of the brute force approach is still O(1), but its time complexity is significantly worse. Cadon's algorithm, by contrast, improves on this by reducing the time complexity to O(n), without increasing space usage. By iterating through the array just once and using dynamic programming principles, it achieves a much more efficient solution. Now we'll look at the best, average, and worst-case scenarios for this algorithm. In the best case, where the array consists entirely of positive numbers, the algorithm still needs to iterate through the entire array to compute the result, so the time complexity is O(n). In the average case, with an array containing a mix of positive and negative numbers, the algorithm still performs a single pass through the array, resulting in the same O(n) time complexity. Even in the worst case, where all elements are negative, the algorithm does not require any extra iterations, it still completes in O(n) time. To formally justify this complexity, we can break the steps down mathematically. Initializing the two variables takes O(1). The loop operates n1 times, and since each iteration requires O(1) work, the total cost of the loop is O(n). Finally, returning the result is another O(1) operation. Combining all these steps gives a total time complexity of O(n). For space complexity, the algorithm requires only two variables, max_current and max_global, both of which occupy constant space. Therefore, the space complexity remains O(1). When solving problems, there are a few common mistakes to watch out for. One major pitfall is ignoring edge cases. For example, if you're working on a problem involving arrays, you might overlook scenarios like an empty array, a single element array, or arrays with duplicate values. Testing your solution against these boundary conditions is crucial to avoid runtime errors. Another issue is writing inefficient implementations. Beginners often start with brute force solutions, which can be fine initially, but for larger inputs, these approaches may lead to time limit exceeded errors. Always look for ways to optimize, such as using hashing or other efficient techniques to reduce complexity. Misunderstanding the problem statement is another frequent error. For instance, assuming that inputs are sorted when the problem doesn't specify this can lead to incorrect results. To avoid this, ensure you read the problem statement carefully and clarify any ambiguous parts before coding. Another common mistake involves off-by-one errors in loops. These can occur when iterating over arrays or strings, such as trying to access an element beyond the last index, which leads to out-of-bounds errors. A simple example would be accessing i+1 during the final iteration of a loop. To prevent this, double-check your loop conditions. Additionally, failing to account for time and space complexity can make your solution impractical for larger test cases. Always analyze the scalability of your approach early on. In interviews, clear communication is key. Start by explaining a basic brute force solution to demonstrate understanding, and then refine it to a more optimal approach. Recognizing patterns can also help. For instance, sliding windows are useful for subarray problems, while hash maps work well for frequency counts. Be ready to discuss trade-offs, such as using extra memory for faster runtime, and ensure you explain how you'd test your solution, including edge cases in stress tests. Now, let's look at some related problems and alternative approaches. For example, the twosome problem showcases how a hash map can optimize solutions for quick lookups, while threesome highlights the two-pointer technique combined with sorting. The best time to buy and sell stock problem demonstrates how greedy algorithms and single-pass solutions can simplify complex tasks. And the product of array except self problem is a great example of using prefix and suffix calculations to optimize computations. In terms of alternative approaches, divide and conquer is powerful for breaking problems into smaller subproblems, as seen in binary search or merge sort. Dynamic programming is ideal for tackling problems with overlapping subproblems, like those involving subsequences or maximum subarrays. Finally, greedy algorithms work well when making local optimizations leads to a globally optimal solution, such as in interval scheduling problems. When choosing an approach, it's important to weigh the trade-offs. Brute force methods are simple and quick to implement, making them a good starting point, especially for small inputs. However, they're often inefficient and unsuitable for larger datasets. Optimized iterative methods strike a balance between readability and performance, making them a popular choice for interviews. They're faster than brute force while still being straightforward to explain. Advanced techniques like dynamic programming are extremely efficient for the right problems but can be more challenging to implement and articulate under time constraints. The key is to understand the problem requirements and constraints, so you can select the most appropriate approach while being able to justify your choice effectively. Great job on completing this session. We covered the brute force approach, its complexities, and key takeaways. Remember, starting simple is often the best way to build a strong foundation for optimization. Stay curious, keep practicing, and I'll see you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!